Hello, my fabulous chemistry minions. Video 9, PBoM, last video of the unit. Hooray. Today is the combined gas law. This is a big old equation that's derived from equations we don't get to do anymore. And those ones are near and dear to my heart. PV equals nRT is the equation I'm speaking of. We can talk about that if you are interested on an individual basis. So, combined gas law calculations before and after for sealed containers is what we are talking about. This is a picture of what I'm talking about going on. So there's a baseline, heat one, and it's going to expand, decrease one, it's going to not, that kind of thing. And that's part of what lab is. There are these three laws, the Charles law, the Guy-Lussac's law, the Boyle's law. You'll see them in lab. But when I put them all together, you get this. Basically, each law, you can see there, if you hold one of those constants or one of those variables constant. So at constant pressure, just cross out pressure and you get V1 over T1 equals V2 over T2. That's one of the laws. And P1 over T1 equals P2 over T2 is one of the laws. And you can just keep going and make any combination of those. Hold T constant, you get P1 V1 equals P2 V2. That's the one that is obviously, because they're not above and below, they're not fractions. That's the one that is inversely proportional, because as P goes up, V's got to go down on the other side, or to save it, right? So those are all three laws. Put them together and you get this combined gas law. You do need to know that the 1 stands for the initial settings, 2 stands for the final settings. I think I'm only actually going to do one problem, okay? And one of the keys to this problem now is temperature must be in Kelvin. And I know when we talked about kelvins before, kelvins talks about total energy. We've never really gotten to 0 Kelvin. We don't want to ever put a 0 in the denominator, but at the freezing point of water, 0 degrees Celsius, you would put a 0 in the denominator here and screw everything all up. So we use Kelvin, okay? Total energy. Kelvin must be used. The pressure and volume units can vary. What I'm going to ask you to do is just keep them the same. If your volume is in milliliters, make sure it's in milliliters. If your pressure, we saw 4 units for that a few videos ago. If your pressure is in atmospheres on the initial side, make sure it's in atmospheres on the other side. This is not one of those problems where I think they try to trip you up, or I will try to trip you up and make you convert. So you need to know the first piece. So temperature must be in Kelvin. If there's going to be any conversion to make this thing go, it's going to be that you're going to have to put that Celsius into Kelvin. We're not going to play games changing pressure units, changing volume units that I can be aware of. I don't see it very often. Here is the one problem I'm going to do for you in video. I'll do another problem or two for you in class and really try to help you with the math. There's one major difference in this math than all the other math we've been doing. So here is the equation we will be using. It is all multiplication and division again, which helps us. And here's the change. I'll talk about it right now. There's an equal sign. Equal sign with fractions. Now I can actually cross multiply like some of us have been wanting to do. Okay, otherwise it is read and recognition from the problem and get the right pieces in the right places. Plug, chug, done. Not that problem, not that bad. So number one, when I look and I see all the numbers, that almost tells me that I'm using this equation, because look, this equation has 6 variables. The problem was going to give you 5. The only real trick with that I've ever seen is they'll say at standard temperature and pressure, which means you've got to go to table A and pull out some of those, that pressure and that temperature piece that they didn't give you. Okay. But they still would have to give you 3 variables, which is a lot. Okay. So let's walk it through. First number I see, 20 milliliters. Yes, your job to know. Milliliters is volume. And it says a gas has a volume of. So this is going to be my initial conditions. So my initial volume is 20. Next number I see, 298 K. It does say there in the reading a temperature of 298 K. So that's going to be my initial temperature. Okay. And then a pressure of 101.3 kilopascals, which we know is 1 atmosphere, by the way. So if I had to convert that one would be easy. But I don't need to convert. They're both in kilopascals. We're good. We're both in Kelvin. We're good. No real big temperature or unit conversions. This isn't meant to trip you up like that. Okay. Next set. what will the new volume be? So now we're on to final conditions, right? If the temperature has changed to 323 Kelvin, so that's T2 now, plug that in there, and the pressure is changed to 50.65 kPa, so put that in for your pressure. Notice the problem's giving me 5 of the 6 variables. So obviously it's asking me to solve for what is the new volume, so that is my V, okay? My V2, and now it's literally just plug and chug. So it says P1 V1 over T1, so it's 101.3 times 20 divided by 298. Boom. So there's my 101 times 20. It's divided by 298. And that is all going to equal P2 V2 over T2. So P2 is 50.65 times X. And then I have over 323. And this is where you get to cross multiply. I'm not going to go into detail right now. I'll do it in class live for you, the detail of how we do this. But what happens is you end up cross multiplying, and that becomes, so my smartboard works, 101.3 times 20 times 323, right? And then you're going to cross multiply the other side, and that's going to be now 298 times 50.65 times X. And then I know that you're going to want to reduce those numbers right off the bat, right? Because I know how you guys like to do math. And you can do that. I'm going to teach you a trick in class that shortcuts the whole thing because I do math fast. But reduce those numbers come to this. So if I multiply the 101.3 times 20 times 323, I got that. And then I multiplied the 50.65 and the 298, and I got that. And then to get that by itself, I divide both sides by that 15,000 number, and I get 43.4. And if you look, the initial volume was 20. The final volume is 43. Between friends, that's in the ballpark. It's doubled, okay? A little over double, but it's not like I got a volume of 4,000 or I got a volume of 0.4, something that's like magnitudes of 10 off. I'm in the ballpark, right? And that helps me just rationalize that I probably got the right answer. So with that, we are done. I'm done with the unit. These problems are literally this simple. You need to do a lot of them. And if you don't feel comfortable over break doing these problems on your own in the practice, well, okay, then don't. Or you can email me. I'll be around, and we'll do them when we get back. We have time. But I'm only going to do one in video, keep the video short, and not do a ton of these because literally it's just plug and chug now. If you know your algebra, you can get through these problems without any problem. And with that, happy unit, and we are done.